Today, we would like to finish parameterizing this spiral. Yesterday, we worked out three different views of our spiral. The XY view where we can't see Z, the XZ view where we can't see Y, and the YZ view where we can't see X. Now, once we set up the XZ view and the YZ view, it started to make some sense because we're trying to make a circle. From the top view, we're trying to make this circle that goes around once, starting off at 3, 0. From the top view, we don't care about Z, we can't see it. And we're going around once counterclockwise. So we're not surprised that we see a cosine show up for X and a sine show up for Y. That's not surprising at all. That's how we make a circle that starts off at the positive X-axis and goes around once. We see that the circle that we're making has a radius of 3. And so let's start just by making a circle of radius 3. We know that 3 cosine t and 3 sine t will make us a circle of radius 3. If we just ignore what's going on with the z, that's what we can get. Furthermore, to make this work, to get a circle that goes around one time, to get this one spiral going up, we know that for this part, we need to make t go between 0 and 2 pi. If x is 3 cosine t and y is 3 sine t, for t between 0 and 2 pi, that will get us one circle. Going around once counterclockwise. So we're just taking the stuff that we looked at earlier, how to build a circle, how to parameterize a circle that goes around once counterclockwise. And now we just have to figure out what to do with Z. Despite our views here, despite these curvy views that we have, the circle, then our cosine, and then our sine, we're really not seeing what's going on with Z. But we can kind of see what's going on with Z if we start labeling things properly. So if I'm just going to pick out, let's see, what's the easiest one to sort out. If we look at this XZ view, remember, we're going to ignore, to write Z of t, we don't care what's going on with X and Y. We care about the relationship between Z and t. We're trying to make Z a function of t. So when t is equal to 0, Z is equal to 0. That's what we're going for here. And when t is equal to 2 pi, Z is equal to 10. Moreover, if I look at halfway, this halfway point where Z is equal to 5, that's going to be halfway through our cycle. So this happens at t is equal to pi. When t is equal to pi, Z is equal to 5. Now we can start to see what kind of function we are building. If we really want to confirm that, so our starting point is 0. When we're halfway through the values of t, we're halfway to the endpoint of Z. And then when we're at t equals 2 pi, all the way through our values of t, we're at Z equals our endpoint of Z. Moreover, we have these 2 points here corresponding to the 2.5 and the 7.5. These happen at a quarter of the period. Now we can really see what kind of function we are building. So if I look at values of t, 0, pi over 2, pi, 3 pi over 2, 2 pi. And then write down our values of z, 0, 2.5, 5, 7.5, 10. We can see that we're just using a linear function. Z is a linear function of t. If we take these values over to our YZ view, we can see the same thing happens. T is 0, Z is 0. T is a quarter of the way through, Z is a quarter of the way through. T is halfway through, Z is halfway through. 3/4 and 3/4, 1 full cycle, 1 full cycle. So all we need to figure out now is the slope. It's a linear function of t, and the slope is the change in z divided by the change in t. Z increased by 10, while t increased by 2 pi. Z is a linear function of t with a t-intercept of 0 and a slope of 5 over pi. Let's make sure it works out at least at our endpoints. When t is equal to 0, z is equal to 0. That's what we wanted. And when t is equal to 2 pi, z is equal to 10. That's going to fit our endpoints. So if we want to describe this spiral with a position vector, we could say r of t is 3 cosine ti plus 3 sine t times j plus 5 over pi times t k. And this is for t from 0 to 2 pi. Question? Comment? Deep thought? Remember what we want to do with this path. We're trying to see, we're going to take this path, we're going to stick it into a vector field, and we're going to see how the vector field affects the path. So this is the path that we want to take in R3, and the vector field will represent the air currents that are either pushing with us or pushing against us, or at least in part pushing against us and partially pushing with us. It's not always going to be going in the same direction. So we're going to want to know the direction that the path is taking. And for that, since we're talking about direction, and I've got a position function, I want to look at the derivative for my direction. So the derivative of 3 cosine t is negative 3 sine t. The derivative of sine is cosine. The derivative of 5 over pi times t is just 5 over pi. And doesn't affect the values of t that we're going to be plugging in. So at each point along the path, this is how we're going to find the vector tangent to the path at any given point. So this direction vector, this velocity, is going to be the vector tangent to the path So here's the vector tangent to the path at any time t. Any questions? If we go back to our views, our xy view, our xz view, and our yz view, we can just take these parts two at a time and draw tangent vectors that we can see. So in this first one, in our xy view, where we almost fit them all. Yeah. In our xy view, where we can't see z, we just really worry about these two direction vectors, -3 sine t plus 3 cosine t. And this is going to be a circle going in the other direction. So -3 sine t and 3 cosine t, if we start off when t is equal to 0, that's going to be a vector pointing straight up. Here at 45 degrees, we're going to have a vector pointing with a slope of -1. Then we'll have a slope of 0 pointing towards the negative x-axis. And so we're going to get tangent vectors indicating the direction as we go around that circle. Note that in our xz view and our yz view, up and down, we can see z increasing at a constant rate. So our velocity vectors, our tangent vectors here in the xz, in the x direction, things are going to be changing. It'll look like -3 sine t, because that's the derivative of the cosine. But in the z direction, we will always have a vertical component of 5 over pi. As soon as I finished drawing all three of our different views, I realized I wanted to draw small tangent vectors on these, and I didn't give myself enough space. I'm like halfway through, it's like, oh, these aren't going to be big enough. But then the me that was drawing at the time said, it'll be fine. And then my subconscious said, no, well, all right, you go ahead and do what you want to do. Any questions? What we've got is our path. We've got a path being described by our position vector. And since it's a parameterized curve, it's got some kind of direction. Then at any point, at a particular point, T naught, let's say, we can plug that T naught into the velocity vector and get a vector tangent to the path. It says at that point, this is the direction that the tangent, that the curve, that the path is headed. The next thing that we're going to want to do is what we originally stated. Hopefully, I've been saying this every day since then, but we want to take this path and we want to put it into a vector field. So here's our path R of T. Here's the direction at some point, T naught. If this is sitting inside of a vector field, if all this is taking place in some vector field, then at this point, there's a vector from the vector field. So also at that point, we've got some vector from the vector field. Now remember, the vector field doesn't know anything about this t parameter. The t parameter is describing what's going on the curve. The vector field doesn't know anything about that. And it's just like the air in the room does not know anything about the fly as it flies around the room. It's just making vectors all over the place. The vector field is given at a point. So I'm not evaluating the vector field at a value of t. I'm evaluating the vector field at a point. But that point is described by the path r of t. So I could say, here's a vector from the vector field at this point t naught. So that's going to be the vector field evaluated at our position vector. At each point, we evaluate the vector field at that point, or we pick a t naught, evaluate the position vector to determine where we are, evaluate the velocity vector to determine where we're headed, and then we look at what's going on at that point in the vector field. So we evaluate the vector field at that point. So we know we have three pieces of information running around here. Where we are, our location, that's the path. Where we're headed, that's the derivative. And what the vector field is doing around us. Any questions? How's everybody okay? Everybody looks stunned. This is the great thing about math, especially calculus. I can stun an entire room and it doesn't cost any key points at all. That's a D&D reference. I think the one person in here that plays D&D is not here today, so. That's okay. I don't need references to land on anybody but me. So that's the big thing. When you get to my age, you'll understand. You'll reference things from your younger days, and no one will know what you're talking about. So what we want to be doing, what we always want to be doing when we're looking at math is, and especially when we're in a calculus class, we want to be thinking about the calculus things. Where have the calculus things appeared here? What other calculus things could be going on? And the calculus things are describing stuff, in particular, describing things like infinite things, but describing stuff. We got to have our derivatives and we got to have our integrals. Those are the three things that could be showing up. Those are the calculus things. We've spent this whole week describing stuff, describing parameterized curves, essentially describing like 4 or 5, no, not even that, 3 parameterized curves in R3. The derivative stuff came up naturally when I said, we're walking along a path, which direction are we going? And it's like, oh, tangent to the path, derivative. As soon as we said tangent to the path, we thought derivative, calculus stuff. I've got 2 vectors here. So we got to think, what can we do integral-wise with 2 vectors? Then we think about what integration is. Integration is multiplication, but one of the factors is continuously variable. Multiplication is a little bit tricky because we have 2 vectors here. What ways can we multiply vectors? We've got dot product and we've got cross product. Then we think about the context that we put this in. We have a path running through a vector field. And the question that I raised at the beginning was how much of an effect the vector field has on the path. Sometimes we're going with the flow, sometimes we're going against the flow. And that question translates to how much of this vector, of one vector, is going in the direction of the other vector. And that tells us that the multiplication that's going to come up is the dot product. This, in the context of the problem, is how we would rephrase that question. Is the vector field helping us or hurting us? Is the vector field working with us or against us? And by how much is it doing that? How much of the vector field is going in the direction of our path? So we are multiplying, and we're multiplying with the dot product. How much of one vector is going in the direction of another vector? That is a dot product question. That is what the dot product tells us. The other calculus question is, the other part of this multiplication business for integration says, integration is multiplication, dot product, but one of the factors is continuously variable. If both of the factors are continuously variable, then one of the factors is also continuously variable. If you have $5, you have $1. It's like, it's in a, a lot of times people don't know how the word or works, but now all we have to do is make this calculation along a continuum. And then we'll be integrating a vector, a product of vectors, a scalar product of vectors. Then we just have to figure out how we can interpret that, which is kind of a question for physics. I'll do my best. Any questions? Comments? Deep thought? I like how math teachers, it's assumed that math teachers are just going to be proficient in all the other sciences. Because like, when you're doing math, you should make sure you can make it relevant to all of your students. Oh, that's too many. You hired me to do math, and now you want me to understand physics and chemistry and economics and engineering. So I'm like, oh, nah. I will plunder those subjects for my calculus class. I'll go grab those subjects and start looking for where multiplication shows up. But I'm not going to be able to come up with a good explanation for some physics concept because not my job, dude. You know what I mean? You need to explain these physics problems. Well, nah, I don't. I need to explain the math problem. And then they're like, oh, but Leach, your whole point is that like, oh, you become proficient in the math, so you don't have to do the math anymore. I'm like, well, that's right. Anyway, you know what I'm talking about? Oh, I also have to do business applications too. Because I can't remember when it happened, but at a certain point, business school says, we should start requiring calculus of our business students. It will make us look fancy. And so they retconned calculus and applied it to business as well. And then when people started saying, that sounds like you're gatekeeping your business school to people that have access to calculus. And then they were like, oh, quiet, you. So it still fits with our design of calculus. Integration is multiplication, but one of the factors is continuously variable. In this context, our multiplication is a dot product because we want to know how much of one vector is going in the direction of another vector. How much of this F vector field vector is in the direction of our path, the direction of our path being described by the derivative. But both the vector field and the direction along the path are changing continuously. They're continuously variable. That means we are going to have to be integrating along the path. This is unfortunately called a line integral, even though we're not on a line, we're on a curve. But it's a one-dimensional thing, so it kind of might as well be a line. You know what I mean? All right, so next week, we're going to look at this problem a little bit more. This is the structure. This is how we're interpreting it. We're imagining a path in a vector field. How much of the vector field is in the direction of the path at every single point? Then we're just going to add it up. I should mention that part too. That's the whole thing with integration. Integration is multiplication, but one of the factors is continuously variable. So we're going to break it up into little bits and say this is the situation for some small change in t. And then at a little later date, t naught plus the delta t, we'll reevaluate the situation. new direction for the path, new vector from the vector field, new dot product. Any questions? Comments? Deep thoughts? Earlier this week, more homework has showed up, so make sure you start getting caught up with all the homework. That's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend, and thanks for playing.